Hi, good morning. So, more of you came, or you came earlier today, or both. So, we're going to talk about transformers today, and from some discussions at the end of the previous lecture, it sounds like some of you are already familiar. There were questions about relation of transformers and graph neural networks. So, it's good to say that I'm including also some slides from a professor in University of Maryland that has done a great job with explaining the basic architecture. So we're going to use that at the beginning. So transformers. Okay, so they're mostly known as sequence-to-sequence models. Yeah. Yeah, but I think it's better. That's what I did, but it's still on. So yeah. Okay. Sequence-to-sequence model in the task of machine translation. Okay, we get a sentence from a language. Sasa, it seems good. Maybe there is a delay. We take a sentence from a language and we translate it into another one. So it's a sequence of words, it's a sequence of elements mapped to another sequence of elements, right? So it's like a sentence goes in the model, another sentence goes out in a in a different language. Okay, so of course towards the end of the lecture that we see that there's very high flexibility, so it's more than a sequence of elements. So our starting paradigm would be, as I said, example of machine translation. Okay, so we're going to be explaining understanding the architecture today through this task. So a sentence goes in, and first we start with what is called an encoder. Okay, we get some representation of the sentence, some representation actually of the words that the sentence is composed of. Okay, so we expect to have semantic level representations of the input, and then there is another component that is called decoder. Now we go from this latent semantic representation back into predicting, the output, which is the translation, the sequence of words in another language. Okay? So typically we start with a very specific symbol. Yeah, it's a kind of not a word, but like it lives in the space of words as well. It's the start of the sentence, and then these models work by seeing what is the current input and current output, no output so far, and predict the next word. Okay, and then now we have a small part of the output. All this is fed to the model to predict the next word that is the most likely to appear given the sequence of that we have observed so far, and so on. Yeah, and so on. And other than all the works or punctuation that is part of this output space that we're making predictions from, there is also a symbol to signify that that's the end of the sentence, that's the end of the sequence, and we're done with mapping this input in the output space, which is another language. Okay, so this way of working is called autoregressive. Okay, autoregressive because every single output of the model is performed, is predicted given the previous outputs. Okay, so it conditioned every new output to the previous one. So and maybe the term regressive there is a bit reminiscent of for historical reasons. It's not, for instance, here it's not a regression task. It's actually a classification task that every next prediction is a class, it's a word out of a codebook of words. Okay, so first let's take a look at the specifics of this encoder. Okay. So the input is a sentence, the input is a sequence, but a sequence of what kind of items? So the first thing that always comes in, now that's specific to natural language processing applications, is the tokenization. We split the sentence into its parts. Okay. And there's different tokenizers. It can be that like every single word is a part. is a token. That's a terminology that is used typically in transformers. Or there is also different tokenizers that split the words based on subwords that are the most frequent based on some analysis in large text corpuses. Okay. Yeah, and every word now has a unique ID, and all the composition of all the words we're using is our codebook. We're encoding these ones based on their ID with simple one-hot encoding. Okay. Of course, this one-hot encoding is some simple indexing. Okay. It carries no semantics about the words themselves. Okay. And that's what we're going to achieve with actually learning a representation for each of these words. Okay. Here we can represent this by an embedding matrix. Okay, it's one embedding per word. So this embedding has matrix has d rows, which is the dimensionality of the embeddings, and the number of columns is equal to the number of tokens. So there is one-to-one equivalence between every token, every word in the codebook, and the columns of this embedding matrix. Okay. So by doing this multiplication, essentially, okay, if you take the one-hot encoding of a dog, you multiply with this matrix. Essentially, that's a lookup table. Yeah. We say the word is a dog. Find the corresponding column. That's it. Let's see where the dog is mapped, and now we start to capture. We should be able to start to capture some semantics of the words and map them to different parts of the representation space. Okay. Of course, is this simplistic approach of one embedding that we're going to be learning per word? Is it enough to capture the semantics of the words that live in a sentence, that are part of a sentence? So we can consider the example of the word apple. Okay. Apple, if we consider the fruit, then someone expects that it should be somehow in the same area of the representation space as other fruits. But there is polysemy. Okay. You have also another kind of apple, that is the company, that you expect maybe these to be in a part of the representation space where kind of electronics are mapped. Nevertheless, this word is exactly the same token in the codebook, so it corresponds exactly to the same column. How can one deal with that? And the way to go is to use context, which is the same way that humans understand language. If you see the word apple in such a sentence, I bought an apple and an orange, it becomes pretty clear that we talk about a fruit. If you say I bought an Apple Watch, it becomes pretty clear it's about electronics. Okay, so so therefore context matters, and we're going to see how transformers are handling that. So we have all the tokens. We do the lookup step, and we get the representations from the learnable matrix. This embedding matrix. And then they all pass through the encoder, and the encoder is the one that is supposed to be. We can see it as a sequence of encoders that capture higher level semantics, more higher level semantics if we plug them all together. Okay? Well, we start simple, not by yet looking at what transformers do, but you can have a feed-forward network. Okay. This term in transformers it's typically used for a module that processes one vector independently at a time. So that should be a multi-layer perceptron, let's say. Typically when we say feed-forward, we mean a multi-layer perceptron in today's lecture. But this doesn't capture any context, okay? You might end up with higher level semantics, okay, because you keep processing the tokens, but it doesn't capture any context. Okay? Well, You could capture local context by including extra links from the nearby tokens. It means simply you concatenate the tokens and then you feed them to an MLP. So this indeed captures some context. It also captures the position of, this is the word before me, this is the word after me. Okay. But still, this is local context and it has limitations, because then you could actually go and say, okay, I will increase the context. Maybe I will try to capture the whole sentence. So here that means that the output for the first token gets at the input the concatenation of all the word embeddings, and you do that for all of them. Okay. Yeah, here just to be sure that there's no confusion, this is exactly the same component, right? Replicated process in each of the tokens. It's exactly the same function. Now, do you see the problem with what is drawn here? It's a question. Any answers? A lot of? A lot of edges, yeah. A lot of computational, it becomes heavy, right? So you concatenate many vectors. Now this means that the parameter matrix of the MLP will be huge. Okay? That's one problem, indeed. Like, it grows fast. Any other problem? Imagine I feed another sentence. Sentences have a variable length. It doesn't work. It doesn't support that. Okay, so we'll see how this is getting fixed with the so-called self-attention, which is one of the main components of the transformer architecture. Okay, it's called self-attention because there is some attention, intuitively some attention mechanism that checks each word with all other words and checks how similar they are and how the context should affect. So that's the case with here the word, the token apple, yeah, that we would like it in this sentence to move actually closer to the representation of fruits. Okay? Otherwise, when you see this sentence, it should move closer to the representation of electronics. So we have the original, the initial representation, and then this attention mechanism. Now, if we focus on the token apple, there's some similarity in the representation space with simple dot product. So, and it does so also with itself. And this is a scalar similarity, right? It's like kind of like it's a way to measure, to what degree each of the other words in the context should affect the representation of apple. So typically, it's more intuitive to go with positive weight, so positive influence. Something influences a lot, or doesn't influence at all. So that would be zero contribution. So we pass them through an exponential function because of this reason, and then we do some normalization. We sum all the values and we divide by this sum, which essentially does the quite known to you softmax operation for all these weights. Okay, so now these weights sum to 1 and they're positive. And now these weights are used for an aggregation procedure. So the context affects the representation. Okay, so we do a weighted aggregation. So this would really resemble what we were doing with graph neural networks, right? It was just through the neighbors that the graph was indicating. So now there is global context. Okay, we see all the elements in the sentence, and we do this aggregation. Maybe you can imagine also that of course, you will not let the word bot to affect much more than apple effect, so there is a self-similarity here, which is expected to be higher than the other numbers. Okay, and based on that, you get the original representations. You do this update now. X4 now token 4 has an updated representation, and after the attention, the representation of words changes gets adjusted. Okay, with such a procedure. So now apple moved in a different part of the representation space, yeah? based on its context. Different context would move it to a different part. Can you see problems so far? Mm-hmm. Good. Okay, that's a good point. Okay, so maybe I can repeat for the lecture. We rely on the fact that the original representation is good to obtain this, degree of how much should affect that it should be good for such similarity, right? So at the same time, we're using the representation both to aggregate, yeah, and to get the similarities. And not only that, there is also a symmetric process, right? Which maybe in natural language doesn't exist. So when you have delicious apple in a sentence, apple should be more affected by the term delicious nearby it, but maybe delicious should be affected less by having apple nearby. So what is the improvement here? What is the change? Is that now there is a projection, okay? There is a linear operation. We project this by a matrix WQ to obtain what is called the query representation of this word. And then there is a different representation. Now we compute this for all other words. That's called the key. So now there is a learnable space, okay? So it's really handling the comment of your colleague here that we're learning another space that is exactly tailored. Okay, it is purpose to do that, to give us weights that later on will be used for such an aggregation. And it's not symmetric anymore because of the two different projections that we're using. Maybe you can see this coming now. Also, we said, okay, we were relying, on the original representation for too many things. We're also learning now another projection, another linear projection that will be used for the aggregation. So you have an original space, but you're transforming it to learn the influence of or the relation between words, and another to do the aggregation. And that's the updated feature, okay? But there is something more coming in. That's like after the aggregation, there is another, we aggregate and there is another operation. So essentially the updated representation is a summation, it's a weighted summation with these scalar weights of the original features projected 2 times with linear operations. Is this meaningful? No. Okay, it's not, because these are absorbed. Actually, it is equivalent to 1 matrix. Right, correct. It is not meaningful. Later on, we will see why this is introduced there, when we go to the so-called multi-head attention. Or this is meaningful when actually, these are not square matrices that have the same dimensionality. So when WV maps to a lower dimensional space, and then you can go back to a space of the original dimensionality, if this is needed. Again, we will see later on why this is the case. But now in that case, maybe this is now meaningful for the reasons I mentioned, and you can see it as a low rank matrix approximation of the full rank that would do such an operation.
But for this second argument, we could still kind of move the boost matrices together and compute them afterwards on the result, right?
Yeah, we're going to maybe see the main reason why this is happening afterwards. And indeed, there are cases that can be obsolete, but somehow it has made it there in standard implementations, and maybe often you use this WO without be needed. But we're going to come back to it. Okay, yeah. So we're going to do the same for every other token. You see now we have queries computed for token 2, so that we can have the updated representation of token 2. And now we can see that, of course, we need to do the same for all tokens. So we compute queries, keys, and values. This refers to a value representation for all tokens. And now here we compute the weights for token 1 with respect to all other tokens, token 2 with respect to all other tokens. Yeah, so we have stacked here all the keys to a matrix, and we do the same actually for the queries. And essentially we stack all the representations in a matrix, and now there is a matrix to matrix multiplication that gives us the so-called attention matrix. Okay, how much each token attend to the others. Then we talked about the softmax. So now this, introduces here like another standard component, which we divide with the square root of the dimensionality of the representation. Okay, so this also empirically has been shown to work well, but this is also because the variance of these elements is proportional to the dimensionality of the representation. So this is needed to normalize when someone is changing the hyperparameter that corresponds to the dimensionality of those representations here. Yeah, and we see all that in matrix form. Okay, matrix to matrix multiplication, we get attention weights, softmax operation, and now again this can be seen as a matrix form where we multiply the value representation with this matrix. Is it clear with dimensionalities? Maybe we can write things down here that this is d times n if we have n tokens. Yeah, the keys are also d times n. Here essentially they're getting transposed. This is n times n. Yeah. Here n times n, d times n. Okay, we can ignore the WO guy for a little bit. Yeah, d times n. All right. So I'm assuming always square matrices. Yeah, that's why we're staying with dimensionality d. Any questions? Is it all clear so far? Yeah.
I would like to ask, would it make sense, or is it also a possible way to implement this to normalize these queries and keys as is done in the metric learning, or like put these representations on some sphere and then always call it product is
Okay. Okay.
similar to the Euclidean?
Good. So I'm not aware of exactly, a variant or an effort like that, but what if you allow me to come back to this, because later on we might actually talk about linearization of the nonlinear operation that happens inside the softmax. So it can, become a bit more relevant to discuss it there. Yeah. Because otherwise you're saying, okay, what happens if I L2 normalize the embeddings here, and then everything follows the same? And how does this behave? Otherwise, that's what you're asking. Otherwise, that the attention values here would be normalized in -1, 1, because you L2 normalize the embeddings. Therefore, now this is not just dot product. This is cosine similarity. Yeah. Yeah. Well. Yeah. 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 To me, it makes sense. To me, it makes sense. I don't have any, better answer than that, or someone that tried it. But I would also, go that way instead of that. But probably, this it might have to do with empirical observations of, how, maybe stable the training becomes like that, and how, this normalizes with respect to dimensionality, which the L2 normalization would do as well, though. Okay. Okay. Good. So everything now just the same operations in matrix format. So what was presented is the so-called single head attention. Okay. We're going to see why this is called single head. Okay. So what's shown here, okay, exactly what was presented so far. Yeah, attention matrix after softmax multiplied by the matrix that has the value representation. Okay, so the intuition now behind the next step is that maybe there is different kinds of, semantic relations that one should be able to capture. Okay? We said we don't trust the original representation, so therefore we said let's take keys and queries to do these dot products. Yeah? But having just one projection might not be able to learn the different kinds of relations, especially in NLP, right? That you have words that are nearby, syntactic relations, like semantic relations, and so on. So therefore, simple extension is let's have multiple such projection matrices, yeah? And this is what is called a head, yeah? We add a head. So 0, another one, yeah? And we have H of them. And we do exactly the same operation. We obtain keys, queries, values, attention, yeah? And get the updated representation. That was what was represented by X prime before. Yeah? The same for all the heads. So now we have different updated representations that each one captures different relations and is mapped to a different representation space. And at the end, we simply concatenate, yeah, towards the dimension, the representation operation. Okay, so if this was dv, yeah, that means that this matrix now has dimensionality H times dv, yeah, times n. So we're stacking them together. And now, Sasa, that's the case that this WO, or everyone, but it was Sasa's comment, yeah, that this actually doesn't become obsolete and it doesn't get absorbed by the other matrix, because now this operates on all the heads together. So now we're getting these many dimensions, yeah, mapping them to a new representation space. Okay, so this doesn't get absorbed, and that's the main reason why this WO is there, and it's always carried in the standard representation implementations. All good? Any questions? Okay. What is n? The number of tokens. Okay. Before I was, maybe writing it as capital. Yeah. It's the number of tokens, the number of words. Let's say, yeah, 5 in our, toy example here. And that's the so-called multi-head attention. Okay, so that's actually, the major building block of the transformer, this attention mechanism. So we start with attention. But then at the same time, we have also token-wise transformation. So the MLP that processes one token at a time. So we can have maybe a relation now with the graph neural networks in the previous lecture that were saying, okay, you have graph convolutionals that have some kind of aggregation interaction across the nodes, but then you can have node-wise, now here like token-wise transformations. So in standard transformers and implementations, this feed-forward network FFN is a multi-layer perceptron. Okay, and we get the output of the encoder block. Okay, what are we missing? Maybe you saw it because I moved to the next slide. Yeah, what was the big thing about graph neural networks? Okay, what was the one of the important properties that we talked about? Yeah, permutation invariance. Yeah, and when we're talking about the graph level representation, but permutation equivariance when we're talking about the node level representation. The ordering should not matter. You change, the order of nodes. It's arbitrary. It's what the graph structure says. That's really not the case in natural language processing. Yeah. Now, with what we have discussed so far, you change the order and you get the same representations. That doesn't sound the thing that someone needs for such an application domain. Okay. And now we go to the so-called positional encoding. So how can we encode, how can we inform this model about the position, the order of tokens of words inside the sentence? So this is performed with another representation that has the same dimensionality as the input representation, the one that we got from the very, very first processing block, the embedding matrix. So to motivate that, imagine that we have a sequence of 16 words, and we're using 4 bits to uniquely identify them. That could be a way to uniquely encode and maybe inform the model. And what happens here is that that's simply to motivate what is happening next, is that you have some dimensions that are oscillating in a slow way and some others that are changing in a fast way, and all this together gives a way to uniquely identify each of the tokens. But that's just a way to motivate it for maybe one of the more popular version of the positional encodings. Okay, so this is the one that uses cosine and sine functions with different frequencies. Okay, so here k, we can see that k is the position in the sentence. Okay, 0, first, second, and so on. It's discretized. It's an integer. Okay, and we have different frequencies for the cosine and sine terms that are actually changing in a logarithmic way. If you feel that this is the magic number, okay, it is actually tailored in an empirical way at the end of the day, so that this will be meaningful for large enough sequences. Okay. So what you do is that you have multiple such frequencies. You multiply frequency times the position, pass it through the cosine and sine function. And you have as many frequencies as you need to match the dimensionality of the original embedding. Okay. Similar to before, you have a dimension that is changing fast, a dimension that is changing slow. Okay. We're going to continue with the explanation about the whole architecture, and we're going back to positional encodings that are, quite deserve some more explanations and discussions. And then the chosen operation is to add the two representations. So now we have like the semantic representation of a word plus the position. Okay. If this is not necessarily the most intuitive thing, maybe I agree. But we're going to see improvements later on. But nevertheless, heads up information that this works quite well or similarly well with other variants in practice. One could concatenate, and you can see that maybe if you do the math, this would behave a bit differently, but in practice, not really, and concatenation would cost to the follow-up processing because you have higher dimensional vectors, while addition doesn't suffer from that. And then you pass those vectors now, you added the positional encoding, so now the order really matters. And somehow, there is information about who are the follow-up, who are the words that come before, and so on. And then we stack many such encoder blocks. Okay. To get the final output, a few more bits, residual connections known to you from previous lectures, also from the previous graph neural networks that allow to train with deeper networks, handle the problem of vanishing gradient. Now there is a layer normalization operation. Sasha, this was covered? Not really, huh? Not really. Okay. Okay. So, well, if you have seen batch normalization, that's the good news. Okay. So, the biggest part of it is that this acts on kind of a different set of dimensions. So batch normalization acts on the whole batch. So this actually acts on every vector separately here. So it will average all the dimensions of a vector, yeah, compute the variance. So other than that, other bits are quite similar. You compute mean and variance of your input, and then you skew again by the learnable parameters.
So is it like per token?
Yeah, it's per token. It's per token. Yeah. Yes, and it behaves differently at batch normalization during test time, because during train and test time for batch normalization there is a discrepancy, because during testing you normally don't have a batch, but here it's the same because it always acts per token. And even though that was the architecture proposed in the original paper, then a variant, made it in for good, that they moved this a bit earlier. Yeah, empirically observed that it behaves better, together with some theoretical, like analysis about the previous variant suffering more by exploding gradients and so on. So to summarize, practically the previous variant, people needed to do some, warm-up stage during the early stages of the learning, that you start actually with a very low learning rate and then go high, yeah, differently. While this was not needed with this variant.
Sorry, what is the difference? What has moved now?
Just okay. Wait. Up. We went. Yeah, the layer norm was moved to a different spot.
Okay.
Yeah, inside the residual connections.
What I see is that in between the move, the head attention and the feed forward, it's stayed. So basically it has moved from above.
Yeah, inside.
In the little row it
Oh.
stayed, and then if you duplicate this architecture, I imagine, okay, you shifted
No. Sorry.
layers, but then the just stayed also still with no delays. But
Yeah.
what really changed this is where this for the residual.
What really changed is that before it was applied here, now it's within the residual connection. Yeah. So that's.
No, but there was already, before the multi-head attention and feed forward, there was already layer norm in the slide before. Here, it is here.
Yeah.
You moved
Look.
one down, but you put the
No. But this is inside the residual. Okay. So still. Okay. So still both moved. Yeah.
this is the same logic,
Yeah.
This is
So the important thing to, the take-home message is that, this has been empirically verified a lot, that, it makes the training easier, plus some theoretical analysis that, okay, it wasn't just a magic move to do. Yeah, there is. There is in this paper. Yeah. Sure.
before we wrap it up. So about could you come back to this? What was it? Yeah, before you started to speak about the residual. Yeah, the positional encoding that it is added. Are these token embeddings, are they learned?
Oh, no. Okay. Yeah, good point. But we're going to have, like, hopefully another, section later on when we finish with the whole architecture about positional encodings. But there's nothing learnable here, because this is part of the input, K. It is the position of one particular token. And this is handcrafted as well.
Yeah.
And then it's handcrafted, yeah. So
Let me say it differently. So
yeah.
if you go to the next slide, so you say, okay, so here we add the token embeddings and the positional embeddings.
Mm-hmm.
And that's like a heuristic that works well. In some other context, I have seen that like this maybe token embeddings would be learned, and the positional embeddings would be, like you say, by linearly transformed before adding. And then I think if you do that, if you kind of insert these linear transforms here and there, then adding the results of these linear transforms is the same as to say that we concatenate these representations and then do like a one joint linear transform on this.
Okay. My intuition is that it's not exactly the same. Some terms are different. Maybe at the end of the day they can both approximate the same kind of functions, but I think we will lose time. But if we write the math down, it's a bit different. Yeah.
Okay.
Yeah. Because you yeah.
Maybe next question. So I thought about what you said, and
WO and WV. WO and WV. Yeah.
Like the linear transform after the
Mm-hmm.
softmax and the linear transform in the to produce these values.
No, they're both after softmax. Both WV and WO are after softmax. Yeah.
Okay, both are after softmax, but you say that here in this case, if it's multi-head attention, it's not redundant. It still is. You could still move out these V matrices and create an equivalent W matrix.
But then the matrices would be, there would be one big
Yeah.
matrix for all heads, and
Yeah.
you would have a separate V matrix for each head.
Yeah, but here the W matrix is also like as large as there are as many there are heads, so there are these blocks of the W matrix, and they could get multiplied with each one is a separate V matrix. I can draw how it works.
So you're saying that you would come up. Wait. No, because the W. Wait. No. Sasa. No. Wait. You can wait. You can wait a little bit. Maybe when we go back to some other multi-head attention slides, right? Because the output of the V functions is like much lower dimensional. So yeah.
Well, the conclusion is it right? The conclusion from that it's still as redundant as in the single head attention, but because of the rectangular shapes of this matrix, it's just more economical and kind of faster to do it this way.
I think there are cases because of the residual connections that you might have to go back to the original dimensionality. Okay, so depends on how you play with the dimensionality. So if you want to be very efficient for the attention within the attention, and you have low dimensionality there, yeah, because of the residual connections, you need to go up to the same dimensionality. So that's one reason why WO is necessary, right? It allows you to have much faster computation of the attention matrix and the aggregation operation with the WVs.
This W and V, so the V is redundant. It can be moved out and combined embedded into the W matrix.
You're saying that the O is redundant.
In the single head and multi-head attention.
Okay, I think the sure thing is that to map to the original dimensionality, it is needed. Okay, that should hopefully be clear. That's it. Yeah, but if you don't change the dimensionality at all, right, you're always staying with the same dimensionality. Again, I think it is needed for the. It is not needed for the single head attention, but it is still needed for the multi-head. I promise to go back to it, but let's save time for that. Yeah, when we go to the slides. Yeah. Okay. Yeah. Mm-hmm. Yeah. That's a good point, right? But I think in common transformer architectures, maybe someone here can say if I'm wrong. I think the dimensionality pretty much stays the same. Yeah, stays the same. Yeah. Yeah. Mm.
Because now we are arguing about because the dimensionality stays the same, we have this. What if we just reduce the dimensionality would be good, or we increase? I don't know. It's just a question.
Yeah. Well, that's something that in practice empirically you often verify, and it's a matter of the complexity as well. Yeah. Yeah.
It's the same. It simplifies many things, probably.
Mm-hmm.
Like the design.
It's going because it depends on what we call the same. To save time and to have time to cover material, we will go back to it when it's appropriate time. Yeah, we'll see. I know that also now it's appropriate time, but let's continue. Not to break this flow of let's see the whole architecture, because otherwise there is many different bits that someone can. Okay. Okay, I can use that thing here. Okay. Done with kind of the encoding processing part. Context matters, and we get higher level representation of the words. and order matters. Okay. Now the decoding part. Okay, so it was said before, we start with a token that kind of is the first starting point, because we don't have any predicted word so far. So this is going to help us actually predict the first word. Okay. So at high level, see now the decoder as a black box. Okay. So now the difference from the encoder is that we're not only processing this input, but we get information from the encoder part. Okay. So here we're going to be predicting the next most possible word, but taking into account what the encoder indicates. What is actually the sentence that it's getting translated? Okay, and the same is going to happen for all the decoder layers. And then the linear layer here is essentially the classifier. See, it happens even if I'm not using my hands, so it's not me. Or maybe it will come back, right? Hopefully. So essentially this linear is the classifier. There is a softmax. It's back, yeah? Always intense. So, yeah, maps, to class probabilities, word probabilities. So, what is the token? It's most likely to be the next token. Once this is predicted, now, second, the process repeats in the same way. Too much clicking. Okay. Good. So, what happens inside this black box so far? Multi-head self-attention, identical way to the encoder, okay? So, I'm attending to the predicted words so far. We're going to explain, how this happened, but like, so it was a fully connected thing, right? Every token attends to all other tokens, but we talked about making predictions in an autoregressive way. So we condition on the predicted words, so far, input and predicted words so far, to make the new prediction. Okay, we're not predicting the whole translated sentence in one go. So that's not the fully connected thing. Yeah, okay. It's not the thing that we need. Okay? Because actually what we would like here is that the first prediction only depends on this token. The second on that and the previous one, and so on. So this depends on all the previous ones. And this is some kind of masking operation. So the attention matrix is an n by n matrix. So now we need to kill some of the attention weights there so that they don't affect the output. There was some weighted aggregation, so we need to set them to 0. And this happens with such a masking here. We need to mask this part, which is in practice performed by adding minus infinity. I think I kind of killed my slides at some point, so it was supposed to be saying here that this mask has minus infinity for the ones that we want to kill. Why? Because then there is a softmax, therefore these are converted to 0. Okay, so it would be essentially the same as if the mask was having zeros after the exponential. Okay, exponent of minus infinity then gets a 0, fine, 0 attention. So for some reasons I think this indeed might be implement it. Maybe someone can confirm with minus infinity, even though it feels that maybe, like this can be more tricky to handle than actually having the mask of 0. So I don't have necessarily a very good explanation with respect to the implementation here. Yeah. Mm.
Should we think of the training phase specifically if you discuss about this masking?
Good point. We're talking, let's say, only about the training phase with this masking, okay? So this is the masking. Why is it done only training? Because during training you have the whole sentence and you need to mask it out. Yeah? During testing, maybe just to finish with the training part, is that, well, a good byproduct is that actually when we do that, we have multiple tokens, to apply the loss separately on them. Cross-entropy loss, it's a classification task, cross-entropy loss on separately on each of them, and we sum all the loss values. So we have multiple predictions for which we're optimizing during the training phase. So good point. The masking is needed for the training, where we have the ground truth and we have the whole sentence. During testing, there is some kind of bad news. You make a prediction, and then you know what is the next token, and then you can do the lookup, take the representation, and include the process. So actually you need to repeat this process after every token is predicted. So that sounds kind of more costly. Yeah. Yes, so it sounds, more costly. Nevertheless, autoregressive models, for some tasks are working so much better that this is the way to go. Plus there is some always efficiency tricks. There is, papers on that about caching. For instance, like you can think that a new term comes in and we need to update the representation. So we compute a query for this, but we need the keys for all the other ones. And we can cache the keys from the previous steps. And then we need the values to aggregate, and we can cache those as well. So there can be some savings during inference as well. That is not autoregressive. Okay. No, actually, yeah, there are also models that use quite similar architecture, but are not autoregressive, and predict all the terms at once. Coming to that, So at the end of the day, it seems that they have benefits in different kinds of applications, and some have made it here, some have made it there. Okay. Everything so far the same. What is the different part, that we didn't talk about yet is that, we said somehow this decoder should be informed by the encoder. And that's the so-called encoder-decoder attention, okay? By the way, maybe the encoder-decoder terms can be confusing. They're really specific to this, to such a task where, transformers were originally proposed. But yeah, they have made it and they have stayed. So that another way commonly to call this part is it's a cross attention, actually, this encoder-decoder attention, the new thing. Why is it a cross attention? Because now we have queries for the terms of the output, but keys for the terms of the input, from the encoder. And there is attention between those, and that's why it's called cross attention. Self, it was like we have a set of elements, a sequence of elements, and everything attends to each other. But now it's cross. We have a different sequence that will attend to another one. Then the values come from those, okay? So actually, this representation here, the next word to be predicted will be transformed based on what the input says. We're transforming the input, So pretty much same architecture, but now you have to understand that it's two different sequences and they play different roles. So one is used only for the queries actually, and the output representations correspond to these tokens. So we feed 2 tokens from this sequence, we get 2 tokens in the output. Maybe you can just wave your heads. Confusing? Is it clear enough? Maybe some of you, it seems you might have seen it somehow already. Okay. So keys and values for the cross attention part, yeah, because there is also self attention among these. Therefore, the cross attention come from the encoder. Okay. And now maybe something to keep in mind was is that maybe there is a problem here which doesn't exist in different kinds of architectures. That this is after a deep stack of processing layers, right? So quite high level semantics, and then we're supposed to match it with the first processing block. So it seems that there is some kind of discrepancy here. Yeah, that these words here, these tokens, yeah, are just processed with one transformer block. So kind of, you know, the intuition is like lower level semantics, and they're going to be matched with something that is the much higher level. So this kind of architecture, encoder decoder transformer, is quite standard for machine translation. Okay, that's why we're presenting it for this one, or for other tasks like question answering. Yeah, you have a question and then an answer comes. So the summary maybe is that they're pretty common because they're better for cases where there is an asymmetry between the input and the output. So that's translation, one language another language, question and answer. So well, apparently it turns out that Google Translate with the T5 model after year 2021 or something was using or is using such architecture to perform such a task.
When we use this cross attention with this encoder computer representations, is this keys and values extracted from the encoder as they are the same for all of the layers of the decoder?
Good. So if I understand the question, you're saying if for all the levels they have the same representation. No.
If you go in the decoder
Yeah.
in the self attention, then this will be different sets of
Yeah. Right. No.
projections.
It is different.
Bounded everywhere.
It is different. So the input is that. The input is the output of the whole encoder stack, yeah, after the layer L, but then they are transformed each time with different K and V projections.
So
Yeah.
you confirm. So
Yeah.
if we want to attend to this encoder,
Yeah.
then we still will do it differently.
Right. Because
Every level.
otherwise, if I understand your question properly, this would also restrict maybe the query representations to be in somehow similar space if the other side is not changing. But every time
Yeah,
it is changing. Yeah.
because here you would draw it as the same stuff goes to all of the layers.
Okay. Yeah. Fair point. It's maybe confusing, but this is here. I'm drawing here. This is the fixed part that always comes in, and then it gets transformed per layer in a different way. Yeah. Good point. Okay. And then, okay, so actually maybe to motivate it a bit by what I said about this kind of discrepancy, the high level representation matched with low level representation, but not only that, you have also decoder only architectures that are really the standard choice for tasks such as text generation or multi-round conversation, which means ChatGPT. Okay, so ChatGPT behind has a decoder only architecture. So now there is not this asymmetry of I give a question, give an answer, and we stop there. Okay, or I give a sentence, translate it, and we stopped. Okay, so in practice, okay, one thing, see, empirically this works much better there, but there is also practical difficulties. Imagine that there is a chat, okay? And as I said, there is one question and one answer. If you stop there, the previous architecture seems to be the case. But then this goes on and on and on. So that means that the input keeps changing and you will need to be processing again with the encoder. So for the second now question, yeah, the given input becomes first question, first answer, first question. So you need to process all that with the encoder that was not processed before. Only the first question was processed.
Say there is not just the decoder only transformer on ChatGPT because you need to have the question first. I mean,
No. Okay. No.
Operates as just filling in after the question.
Yeah.
Everything is the
Yeah. Yeah.
everything is the input of the decoder and just adds
Uh,
new
and what to clarify, there's no cross attention anymore within the decoder, because there is no encoder part to inform about what the encoder says. So that's why I said, for instance, like here it can be confusing, the terminology encoder decoder, because now this decoder, this part is exactly identical to the encoder, but has the linear part that is actually making the prediction, so it maps in the output space, therefore it's called decoder. Okay, but
You could also draw it like with
Hmm.
decoder and
yeah. So here indeed, as it was said already, the question is part of the context. A question comes first, and then what follows next? Okay, what is the next most likely term? The answer comes. And there, I believe you might have been all exposed more or less to prompt tuning. Then that means, okay, like someone needs to figure out what is the appropriate context that helps the model to give better understand the context and give the best answers. But the main reason I'm mentioning that, what does that mean, by the way? You maybe give a sentence, the prompt tuning, you give a sentence, and then you want the model to perform sentiment analysis. Okay, this is a review. Does it sound positive or negative? And then you give the sentence, and then you ask the model in different ways. Is this a good review or not? And then you might figure out, okay, what is the impression described in this blah 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 blah. This is the prompt tuning. The prompt is the way you describe the task. Okay, so now this becomes much more very flexible, and prompt tuning is meaningful. Sorry, prompt engineering. I was using the word prompt tuning. I want to say prompt engineering.
But anyway, when you talk about this, there is already like further training involved. It's not just like train like this. You need to train further with reinforcement learning to get the answers. And is it not just
Well,
like
Yeah, I think
from prediction?
we're today we're not really covering this part, and we're not covering. I mixed up the terms. It was prompt engineering, maybe to come with an interesting part that now we can fit different number of tokens in the input and in the context, and then there is a so-called prompt tuning. So far we were maybe what you've seen is that we tune a model by tuning some of the hyperparameters for another task, but now you can have a prompt, a token that plays the role of steering the model to do different things, and not anymore by tweaking the internal parameters, but just the parameters that correspond to this special kind of token. So that corresponds to prompt tuning. So instead of trying to figure out the best prompt to give to the model, you kind of give some tokens, and these are the only learnable parameters which are at the input. That makes them very different than other models that were discussed so far, like CNNs and how someone is tuning them. Last case, encoder only, even though it's the same as the decoder, but now this is for different tasks. So we can use actually transformers also to represent the whole sentence, or the whole set of items, whatever these items are. So this is the corresponding thing to the graph level representation in the previous lecture. And these are common architectures for classification of text and so on. And typically we don't need the output, the representation of all the tokens, but there is something that corresponds to the global level representation. So typically you remember this start of the sentence token. So because this interacts with all other tokens, so we often treat it as the global level representation of the whole sentence or the whole text. Now, if you think, okay, but actually, maybe when we predict the next word, what I didn't mention is that we have lots of training data out there. Okay, you mine from a domain and you have training data for free. But in classification, you need some kind of labeling, so that's much more costly. How can I learn such a big model? So the pre-training kind of here differentiates, and often someone takes sentences, masks something. What did I do? How are you? yeah, okay, maybe I wanted to mask this one. Fine, yeah. Let's say we mask this one. Yeah, this doesn't exist. Ah, no, it's today. How are you today? No, I think I know what I did. I wanted to mask this one, okay? I wanted to mask this one. So imagine that this is masked, yeah, and we're trying based on the context to predict it at the output. So that's a task where we can get trained data for free, and you really force the model to learn how the context affects, yeah, and to learn the semantics of a sentence. And then after this pre-training, you go to a classification task, and you take this, you feed to a classifier, and you fine-tune the model. Yeah. Okay. Heads up information. So we're going to go back now a bit to multi-head attention, positional encodings, scalability of transformers, and so on. But that was pretty much, you know, all the architecture and the intuition behind the mechanism of transformer architectures in the context of natural language processing and some of the popular tasks. Okay. Sasa, now is the time, I think. Multi-head attention. We're going back, okay? just for a few extra comments, and this is also relevant. So, just repeating the same things, okay? 3 tokens in the input. We project 3 times, okay? Using square matrices always in this example to get keys, queries, and values. Matrix to matrix multiplication to get the attention matrix. We do softmax to get the normalized one times V times WO to get the output. I think we agreed. In this case, in the single head, this is not needed, especially when we're dealing with square matrices. Let's go to multi-head, but a specific case where we work with the same number of parameters, okay? I think this is kind of interesting because you have the model of the same size. Let's see, is this multi-head attention meaningful? So what happens actually here is that is as if you split the projection matrix here in 2, okay? And then what do we have? Queries of the first head, queries of the first head. Now we concatenate them together, okay? So if we concatenate them, one head is responsible for half of the dimensions, one subspace, the other for another subspace. We do the same for keys and values. What's different here? Okay. 2 attention matrices, okay, with the corresponding subspaces. We project, and again the value matrix here, it is split in 2, okay. We concatenate, and now we project with that. So as I was saying, this is the one now that is merging the dimensions. So Sasa, in this case, okay, of course, it depends on the settings and the number of parameters, but we have 2 models with the same number of parameters, and there cannot be such an equivalence because this is not, I think, in what you were saying, you were assuming that this is also square, and this is also square, so you have more parameters. No. Yeah.
I'm saying that the B matrix is redundant, that it can be taken out and multiplied with the W matrix in this.
But you need different V matrices for every attention, and if you do that, you will need a square matrix, so you have more dimensions, so you're talking about another setting. You talk about a larger model that you can do that with, and I agree in this case. Hmm?
I'm saying that we can do it preserving exactly the same dimensions and exactly the same model. The W matrix might be larger as a result in the end.
Yeah, that's what I mean. It's larger. It's larger, so you have more parameters. Yes, it will be larger. I agree.
In the end, it is
Yeah. Yeah.
like, okay, representing some linear transform, which is
Yeah.
with this low rank property that it is a product of 2 rectangular matrices rather than a general square matrix.
Yes. So now maybe all the confusion comes by the fact that normally, I keep looking at this corner to guys that have worked a lot with these models, that I think normally the dimensionalities of those 3 guys are, are the same. Yeah. But this is an implementation, detail, and it doesn't have to be so on, or maybe it's some empirical finding. But okay. So to keep this is, do we agree with that? This is necessary if we're talking about 2 models with exactly the same number of parameters, exactly the same model size. Yeah. Okay, so what I want to point out is that same model size here, yeah, and pretty much similar complexity, yeah. If you put things down, it's quite similar, yeah. In what you do. Hmm. Okay, Sasa, what if I recommend that we maybe leave it for the end, summarize it, and maybe even add it in the slides afterwards, yes, to save some time for the other material.
Just a short comment.
Okay.
So now here, I think like conceptually it is redundant. Yes, so you could still take out all these V matrices and make their product with your green W matrix,
Mhm.
but you could consider it as a sort of some composite linear layer, which is the after processing after the self-attention. So you don't need it as a component of the self-attention. And neither in terms of generality nor in terms of the efficiency. So
Mm.
I would conceptually separate it. So we could have like the self-attention without this double, without the V matrix.
Okay.
And then the result you multiply
Okay.
maybe with linear matrix, maybe with the product of two matrices of the rectangular shape. I don't know.
So you're saying, I expect that empirically, if I set this to identity, I should be getting pretty similar results. Okay, fine. Like let's say I would just trust like a super large community of many people that have been playing with this model that they would have figured out that this is like unnecessary processing. So my understanding is that probably this indeed because of the mixing of the subspaces. No?
Sasha would kill these if I'm
Yeah, I would kill
Oh.
these and take the matrix level.
Okay. Huh?
something like that exists in one of the linearized things. There are some works that set
Wait, if you kill these, then you mean that the aggregation acts on the whole space and not on subspaces.
Yes. Yeah, you
And
don't spend the A or no, the like yeah, the whatever.
no, I'm trying to think now because we have Bill here in the front row that has done, experiments quite similar to that. But okay, okay. I think that's very debatable because we only we would only know if we run an experiment that is comparing apples to apples.
name now that was trying to simplify the transformer blocks
Mhm.
at some point, and one of their observation was that you can remove value matrix or like set it to just to give you the like you don't even learn it, like kill it completely and just keep the WL, but
Mhm.
it was something that was tried in one paper. They tried to show it works as well, doesn't have issues with the training, but it never caught up in anything.
Okay, we haven't had it in the domain.
Yeah, so it's maybe unclear.
No, from this kind of in terms of too much dimensions, you sort of need some matrix there.
Yes, to match the dimensions, yes, but like to just
So in my construction, if you take it out and multiply with W, you will get a larger matrix.
Yes, but I think it's been said before that despite this formulation in general, still like the square matrices are mostly used in practice, right? As you said. But from what I understand, this is still used despite the fact that they're square and it's not really that is that evolved, right?
Okay, I have a proposal. We move it to the seminar. You will have an assignment to figure out what happens with the V and W matrices.
So a point to make here is that you have these two variants that have same model size, quite same complexity. Maybe this because of the differentiation matrices needs a slightly small amount of extra memory. But is it worth going for the multi-head attention? So I think the answer is in the end empirical, and many times yes, many times no. Okay, so you have Bill here like that is working on something that if you compare. This is number of heads and performance. It was really going like that. And we have other tasks. Yeah, you increase. No, maybe I didn't. That was. No, that was like, no, I drew something wrong. I drew that this is model size. Yeah, model size complexity, and it grows like that just because, you know, each dot has more. So this was performance, and this was model size, so it doesn't change. So this is something that you don't easily observe, right? For exactly the same, yeah, it decreases like that. But it was a very specific task. We have also other tasks where multi-head is the same as single head and so on. So now I want to move a bit faster, but otherwise, yeah, there is also some analysis that actually tries to see whether, like in NLP, different heads are really capturing different kinds of relationships. And yes, they do. Sometimes about, you know, the proximity of the words, other syntactic relations, and so on. Okay. So, okay, one thing that was in the list to revisit, we did. Okay, because I promised we're going back to one thing, and then there is, I think, one more. Yeah. Positional encodings. Okay. So these fixed ones. Okay. There was nothing to learn. It's a hard-coded function. And now here we can draw the different dimensions, and you have dimensions that oscillate very fast. So this is the position, and this is the value of the dimension edge of the dimension, and others that, with respect to the position, right, with respect to k, and others that drop pretty slow. So for appropriate tuning of those values and dimensionality, you have a unique identifier of every position. And the intuitive idea is that you have these low and high frequencies and the dimensions that oscillate in a very different rate, and that this allows you to capture, you know, long and short term dependencies by, you know, with respect to the positions within a sentence. Okay, and the good thing is that this can be defined for any position. So if you're about to extrapolate to go to longer sequences, this can be defined, but of course typically there's some capability of, you know, the transformer internally operating well if you go much further, or to interpolate, which doesn't happen in NLP, but it happens if we go to other domains like the image domain, that you have images of high resolution all of a sudden. So, and you know, there's some intuition here that, you know, this should be able to learn and operate on relative positions. So try to motivate this a bit more. One can see that if you get the embedding of position k, yeah, and the embedding of position k plus a shifting plus delta k, yeah, that there is a linear transformation to go from one embedding to the other, yeah. So you multiply with this matrix that depends on delta k. So this really doesn't matter of, you know, the absolute positions, just like on the relative, that they are that far apart. And again, the intuition is that we feed these to processing blocks that have some linear layers, so therefore, you know, you expect that the model should be able to capture something like that. But of course, this holds only if you try to explain how one processing block works. If you go further and further, you know, nothing like that holds, because these embeddings then have been processed with, you know, so many layers and non-linearities and so on. And maybe an extra way to understand these positional embeddings is that if we try to see the similarity between those two, based on the dot product between such embeddings, so this is a function that decreases like that, while the difference in the position increases. So this is position 0 versus position k. But actually, if you do the dot product, you will see actually that this is like a shifting variant. It's a stationary kernel. It doesn't depend on where the exact positions are, but it only depends on their difference. Okay, so that's a bit more again to explain why, you know, the intuition behind that this should be able to capture relative positions. Skipping, okay, or going extremely fast is that, okay, they did something similar for learnable. Okay, there is also learnable encodings that now, for every position that you have, you will learn the encoding. Less interpretable, okay, briefly to say, and you have bigger problems with extrapolation, right? You cannot extrapolate, and in practice, interpolation seems to work to some extent. So if you had, you know, like let's say you were processing an image with resolution 100 times 100 pixels, so you had 100 positions, and then you want to go to 200 times 200, you actually just need to interpolate the missing positions, and this seems to work up to a reasonable extent. I would interpret it is that maybe if we zoom here, near the diagonal, it's more interpretable. Maybe it's something that decreases also, but like when you're going very far, it's very arbitrary. Yeah, but I wouldn't sign on that. I wouldn't. Yeah. Yeah. No, this compares like every position with all other positions. It's similarity matrix between 1000 positions. So on the diagonal is a self-similarity. So yeah. So this is the thing that I plotted before, just now in the similarity matrix. So that's why you see, Jan, maybe like the most relevant part is here also for the sinusoids that we're talking about. But okay, I think the take-home message is like less. Yeah. Oh. Trying to think. Relative position. Okay, so for the next lecture, not really. I think we're going to maybe compress a bit, go fast. So okay, or we can take 5 extra minutes, even though I think that's not the most appropriate for your schedules. Okay, so not losing time. Before we said okay, there is some intuition, because when you do dot products in the very input, relative positions matter, that the previous encodings will capture relative position. But there are also cases where we improve the injective inductive bias by different design. So here that's the vanilla aggregation, okay? Updated representation of token I, aggregation over all other tokens by weight. If we analyze that, what was it? Like projection with WV of the feature plus the positional encoding. Now, instead of having this guy here, we add something, yeah, because this depends only on position J. We add an embedding that depends on the relative position. So now we learn more embeddings because it's a pairwise. It's a pairwise thing. Yeah, no, actually, that's not accurate. We don't learn more because it's a relative position. So one could even write it down with relative positions. That's like one is position I and the other is I plus delta. Yeah, so that's what matters. So if we're talking about the next token, there is one vector that is learned here. If you're talking about the second next, another vector, and so on. Write the previous one, another one. So the way we do attention here depends on these vectors that now are explicitly depending on the relative position. And we do the same for the attention. So this was for the aggregation and the way that values are computed. So what is, in terminology of graph neural network, what is the message that you're passing to me? I will transform the message based on the position. And here, what is the attention that we have with each other? I will transform the attention based on the relative position. Okay. And then the authors of this work also clipped, the importance of that after some distance. So they were not using any positional encodings, assuming that it doesn't matter so much. I think the rationale is the increasing the inductive bias that you inject by the design. Normally, what do? We have, some prior knowledge that it's not about absolute positions, it's about relative positions. And then this is designed differently to increase the inductive bias. Before, it was like kind of, you hope because of the construction that it will be relative positions that matter. Here, you only inform, your signal only encodes relative positions and never absolute positions. Yeah. Mhm.
but also all kind of other stuff.
Okay,
And maybe
that's
then becomes not only
okay.
becomes dependent on the position and some where ways on what ways.
That's a very good point. So, but if I follow properly, it means this, what you're saying, happens for this guy here because it only affects the scalar attention. But still, this is something that you will propagate, okay? Because still it affects the values and you aggregate. But if I recall correctly, in practice, this is much less important than this one. So it goes to where you're saying that you're not affecting the representations that flow, you're only affecting locally the attention values. Yeah. So it links with some results, I think, in practice. Okay. I will choose, even though it is kind of one of, the ones that have made it over time, another relative positional encoding, but I think one can even kind of follow from the slides afterwards just to, talk about 2D, relation to 1D to deconvolution and graph convolutions, okay? We did the same last time relating to deconvolutions with graph convolutions. Now for simplicity, actually, I decided to switch the example to the one-dimensional case, okay? So, what do we have here? Like, 3 elements, in a sequence, it's one-dimensional signal and the corresponding representations. So, in 1D convolutions, as the same as we were doing the other time, the output representation for node I is a projection of all those, a different projection based on their position. Yeah. So 3 different projections and aggregation. In graph convolutional networks, okay, we have a graph that connects the nodes now that have their representation. And the difference is that, now we're projecting. We are projecting each representation again, but it's a weighted aggregation based on the weights that the graph indicates. In attention now, okay, the formulation here is pretty similar to graph convolutional networks. Maybe you saw this coming. Yeah. What is different is that now these are not fixed, and these are learnable. Okay, and they depend on the specific pair. So the other time there was a question by one of your colleagues, maybe you, is there a comparison out there that compares graph convolutional networks and transformers? Actually, my summary in that is that I was not able to find one, comparison under the same settings, but I think it's because of graph convolutions are still the de facto choice for fixed graphs where the graph is part of the input, like the molecular graphs. While, in attention, that's not the case. You always, learn the relationships again and again in different ways over the different layers. So it seems that there is a smooth transition between one and the other. Okay. Why? Because, this is fixed and this is learnable. Now, if you fix it, you actually become equivalent to graph convolutional networks. But of course, there is a lot of other bells and whistles, in the standard architectures that actually they're also transferable. Also, the other time we're talking, okay, add some MLP layers, add residual connections. So there's really a smooth transition between one and the other. Okay. So, and graph convolutional networks, because of the lack of positional encodings, which you can find now also work in the literature that do something similar, they were transforming every feature with the same projection matrix, W, and we said that's a limitation, right, compared to the 1D or 2D convolution that can really process differently based on where the neighbors are. Well, this is changing in transformers because of the positional encodings. So now it is not exactly, W that does the work, but is the way that we design the positional encodings that make position matter, and the way we process depends on the position. Okay, so this is like a more general point of view that another way to see transformer blocks, attention blocks mainly, is as in-context mappings. Okay, so that you take a vector and you condition the processing on some context, and the context typically is given with another matrix, with another set of vectors. And now the way we process this depends on the context, which is not what happens with multi-layer perceptrons that will process xi independently from any other element. And this formulation actually makes it very generic. Now, you know, the context can vary on different tasks. Please wave your heads. You're okay with 5 extra minutes? Okay. If you open the door and run out, fine, because there's like, you know, the option of not going through. Okay, scalability issues. The attention is heavy. Yeah? It's quadratic to the number of tokens, to the number of elements in your list. So, going briefly, there have been variants that say, okay, I will actually, like, the far away matter much less in many tasks. I will not do the full attention matrix. I will do something like that. Or I will dilate this. I will leave some, you know, gaps. Or to improve that, I will say, okay, I will only attend to the local neighborhood, but I will indicate some tokens as global aggregators. So now one token is responsible to interact with all others. And this is a way kind of to try, you know, to exchange information with all tokens and then locally with a nearby, but you have many different layers, so the receptive field actually increases because of that. The problem is that, okay, it's tricky how to implement and get improvements. So in practice, yeah, there have been some implementations that get time and memory improvements, but not all different implementations of such ideas can really benefit. A more interesting concept and observation is the following. That actually the softmax, yeah, because of the exponential there and the nonlinearity that it has, it gives us hard time in terms of complexity. Why is that? We have 3 matrices involved, okay? And first we compute the attention matrix. We do the softmax, yeah, and then multiply with the value. So in terms of the number of elements, this is quadratic, yeah, because of this guy here. But if there wouldn't be exponential there, and there would be a linear attention weight, yeah, let's say we forget exponential, and this is just a dot product, then someone can change the order of the operations, and first multiply those two, and then the result with the queries. And now, this is linear in the number of elements. Where this is helpful? Not everywhere. When the sequence length is much larger than the dimensionality, yeah, which in many tasks it is. You have, say, you have NLPs where their context, yeah, as we call it, the sequence length is like tens of thousands or up to hundreds of thousands of tokens. So there, such an idea can really matter. One paper did quite simply say, okay, now let's have some. Now these are keys and queries. Let's have some mappings phi that make the vectors positive. No, I'm going too fast. Some mappings phi so that we achieve what we want, yeah, but good attention, but the operation remains linear. There is no exponential. And the intuition here and some empirical observations is that what we want is the non-negativity, which also makes it very, you know, more intuitive. You do the aggregation, and whatever should not affect you, it has 0 weight. Okay, it's not negative weight that will map you to a different part of the representation space. And the peaky distribution because of the softmax, yeah, the concentrated energy, attention values that are large only for a few tokens. And then for the non-negativity, they tried simple things. Yeah, actually, we see an experiment here that when they use this as identity, but there's no exponential anymore, the model performed very poorly compared to softmax. So this is linear, but doesn't perform well. And then just the ReLU already was a game changer. The ReLU makes, you know, positive vectors. You have only positive attention values. Okay, and apparently that did a lot of the work and linearized attention. Now then, for the concentrated energy, actually this paper, you know, some time ago did something very similar to the relative positions, but did it explicitly by multiplying the values in the attention matrix with a function that depends on the relative distance in terms of position in the sequence length. So if you're nearby, I'm multiplying with something large. If you're very far, I design a function that goes to 0. Just to try to do something like that in maybe not the best possible way. More interesting work is that builds on random feature maps. Okay, random feature maps that approximate nonlinear functions just through a dot product. So this is nonlinear, but at the end of the day, we can get some mappings that, with a dot product in some other space, approximate this. And there is a lot of nice work in the New Rips paper that I think even won the Test of Time award, that designs such feature maps for many functions, but they don't have the non-negativity property. And then they explicitly design something that is appropriate for the softmax, which is actually such a mapping. Now you take your vector x, you project it to some random vector, subtract some constant, and then pass it through an exponential. And this gives you one scalar, the first dimensionality of your vector. You do this for many projections, and that's what you get. And this allows you to linearize the attention. And we see here as the sequence length grows, the improvements are the gap between the solid line and this line. Yeah. That, of course, that the gap between these curves in terms of time increases when the sequence length increases. Maybe time for final questions. Could talk a bit about some different applications just to give other ideas than NLP.
So both the ideas about the relative positional encoding and what was here, they really only work with the sequence length would be sufficiently large, right? Because for example, in a small sentence, when I was thinking about it in that context initially, some in relatively small sentence, right? There might be some words connected by words that don't really add any meaning, and those would be closer to the word that the attention would contribute to than the actually useful words.
But can you say, I didn't understand the first part of your, so what is the question then? Or it's not.
To assume that stuff like the relative positional encoding, right, is only meaningful once the length of the input is large enough.
My intuition is that not, because especially we talked about that you saw also this not always intuitive but heat maps, between positional encoding, is that normally it's the nearby terms that are affected the most and not the far away. But I think it can be very application specific, right? Because for semantic level understanding of text, maybe you need the nearby. Now when you do question answering and the context is some long document, you need to be able to really attend strongly to pretty much anything. I think it can really vary. So for instance, okay, we, in the team here, we're working computer vision, and there in computer vision, geometric information really matters, should really matter. And surprisingly, in most of the tasks, we're not able to get any improvements or very small improvements by such kind of positional encodings. But okay, now the interpretation of that is multidimensional, which, maybe brings me to transformers are popular also for vision applications. Now one token is a patch. You split your image into patches, you project them to some representation with a linear operation, and then that's what you process through multiple layers of attention. And typically what you need is a global level token, some dummy at the beginning token that will be your image level representation that you can use to do compute similarity or do classification. And then there are other cases where someone puts such a transformer architecture for images together with transformer architecture for NLP, map them to the same space so that you can compare images and text. That's a popular clip, say architecture. Going more to things like maybe you have seen now you have ChatGPT where you interact with text, but you can give also an image. So how the hell this happens? Actually, there is transformer architectures to do all that behind this. And what happens is that you have a large NLP model that understands language, and you have another image model that's also a transformer and has its own image tokens. Yeah. And now the first step is typically to map these tokens to the space of the NLP, and now images can interact with text. And therefore, you can now make questions that answer what is shown in an image. Yeah, what is this object? Okay, what is the action depicted in an image? So all this has transformers internally, where words interact with words, image patches interact with image patches, and everything with each other. Behind models like text-to-image generative models like Stable Diffusion, you give a sentence, you generate an image that represents what the sentence talks about. Okay, we're not going to follow this complex architecture, but again, internally there is transformers, okay, to generate the images. There is transformers to capture relationships between the patches of the images you're generating, and there is transformers also to transfer information cross-attention now from text, from what is said there, to the image patches. Okay, all this is very high level. A lot of work on time series processing, and probably that's all for today. Good. Okay. Thanks. So next lecture in 2 weeks. As I said, hope you will still all come, or even more of you. It will be much less technical, something at the level of responsible, fair AI, biased AI. Coincidentally, we have also someone, a colleague, an expert that works in figuring out the biases of such models. So we're going to split the lecture with some generic stuff and some of her work. Hopefully, also people from our teams will start, and will be maybe more of an open discussion than just a lecture.